In today's lecture we've carried on talking about the electron. We started off, if you remember, by looking at Millikan's experiment, which was a particularly elegant way of weighing the electron. In this case he balanced the force of gravity on an oil droplet with an upwards force from an electric field. In doing this, and by considering the terminal velocity of the droplet, he was able to come up with a value, with a very accurate value for Q, the charge on the electron. Now this came about because the droplets always contain an integer number of these charges, and by working with enough droplets it was possible for Millikan to work out exactly what n equals 1 for Q was, so to work out the charge for a single charge carrier. So from here he could then go and use Thomson's results for E over m to come up with a very accurate mass for the electron, which again agreed with the results Thomson had earlier obtained and showed that the electron was in fact a particle of much less mass than a hydrogen atom. Okay, so from there we went on and looked at the effect of magnetic fields on electrons in solids, and we saw that when a current was flowing in a magnetic field, then the charge carrier's path was bent, giving rise to a transverse voltage to the direction of the current. This of course is the Hall voltage. So measuring the Hall voltage enables us to calculate a number of materials parameters, including the sign of the charge carrier. Okay, this tends to be important when we're considering semiconductors and wondering whether they're N-type or P-type materials. N-type have electron charge carriers, P-type have holes which are positively charged as charge carriers. Metals in general of course have electrons as charge carriers, so they have a negative charge carrier. We could also work out the drift velocity of the electrons, and we showed that this is quite a small number. Allied to this we worked out the number density of charge carriers and showed that in a conductor this is very high. And this again shows that the electrons are behaving like a gas with a very short mean free path, so the electrons are having lots of collisions, which gives rise to the very short, the very low drift velocity. We can also, if we have a well characterized piece of material, we can also develop a Hall probe, which enables us to measure magnetic fields. So from there we've gone on and looked further at considering the behaviour of conductors, insulators and semiconductors. We saw that we can define the resistance as R equals rho L over A, where the rho is the resistivity and is a material specific parameter. We also defined the conductance, sigma, as 1 over R with units of Siemens. We can see that there are three broad classes of materials. Materials which have a very low resistance, or conversely a very high conductance, which are called conductors. Materials with a very high resistance, or very low conductance, which are called insulators. And the final class lies somewhere in between, which is semiconductors. To explain the behaviour, we've considered the fact that electrons have allowed levels in bands. So for conductance to happen, we must get an electron into a level where there's no other electrons, so the electron becomes free and can conduct. We've seen that in conductors, the Fermi level, which is the level of the highest energy level filled by an electron, we've seen that the Fermi level lies in the middle of a band, so it's very easy to transfer to another level. In an insulator, all of the bands are filled right up to the top, so to get to the next band, the so-called conductance band, we have to supply a lot of energy. The band gap energy is very large, which is very difficult to do and doesn't in general happen. So the electrons can't go anywhere, so conductance doesn't happen. Whereas for a semiconductor, we see a fairly similar picture to the insulator, but the next band is very close to the highest occupied state, so all we have to do is supply a small amount of energy and we can turn what is an insulating material into a conducting material. Hence we can use the semiconductors as electrically switchable switches, which has absolutely revolutionised the way that we work and the way that, for example, computers work. So at the end of this lecture we've seen that the electron exists. It's very small. It's a lot smaller than the mass of the atom. It's got a charge, which is the same for all electrons, which is 1.6 times 10 to the minus 19 coulombs. And we've seen that the behaviour of electrons in magnetic fields allows a wide variety of materials parameters to be found through the use of the Hall voltage. Finally, I've shown you quite a hand-waving, but nonetheless somewhat accurate method of describing how conduction occurs by considering electron band structure. And then from here we're going to move on now. Next lecture given by Chris, we're going to look at X-rays, and then from there we're going to carry on delving into the atom itself. Thank you.